Section 6 has a different character from the ones before it. It starts from a procedure everyone learned at school, eliminating unknowns one at a time, and that one procedure solves 4 problems at once: a basis for a span, the dimension of a subspace, determinants, and inverses. First dilemma. Take a list of vectors and do one of 3 things. Interchange 2 of them, multiply one by a non-zero number, or subtract a multiple of one from another one, not from itself. None of the 3 changes the space they span. The reason is simple. Every one of them can be undone. Interchange twice and you are back. Multiply by a non-zero number and divide again. Subtract a multiple and add it back. Since each list can be reached from the other, each sits inside the other's span. Applied to the rows of a matrix, these are the elementary row operations. Then a definition. The order of a non-zero tuple is the position of its first non-zero entry. 4, 0, 0, 0, 2, -1, 0. The order is 4. Smaller order means fewer zeros on the left. The algorithm runs like this. Among all the rows, find one of least order, move it to the top, divide it by its leading entry, and subtract multiples of it from every other row, so that its column is left with that leading one and nothing but zeros. Then repeat on what is left. Fix on the next order that occurs. Bring that row into second place, and clear its column the same way. Let us watch one 3x4 example run, start to finish. This one needs no interchange, since the first row already has least order. The matrix you end with has 3 properties. Among the first k rows, the jth has the jth smallest order. If k is less than the number of rows, the remaining rows are all 0, and the njth column is exactly the jth standard basis vector. Why are those k rows a basis? Take a linear combination of them. Since the njth column has a 1 only in row j, the combination has exactly the jth coefficient in that position. For the whole thing to vanish, every coefficient must be 0. So those k rows are independent and they span the row space, which makes them a basis for it. Of the 4 problems named at the start, the first 2 are now settled at once. The basis reads straight off, and the dimension is k. The example showed something else too. One of the 3 original rows was a combination of the other 2, which the eye cannot see. After the elimination, it became a row of zeros, and the dimension turned out to be 2 rather than 3. The final matrix is called row-reduced echelon form. It can be shown to be determined by the row space alone, whatever matrix you started from, and in whatever order you worked. Its rows are called the canonical basis of that space.